All right, so hello. Um, so welcome to the Interop overview. So basically, just want to start off saying that with Interop, I believe it is possible that we can write our smart contract systems in a way where we find like the bottlenecks in the smart contracts, right? The most gas intensive places in the smart contract systems, and we like shard them, across many chains, right? This is like a traditional kind of like Web 2 tech, idea where you can horizontally scale your applications. Right today, we still write modular, or we write monolithic smart contract systems. Right, there isn't really much of an idea of like modular smart contract systems. Right, we have modular protocols, but we're not yet to modular applications. So I hope that we can like fundamentally change the developer experience for smart contract applications using this interop protocol as the base. Any questions or like comments or thoughts on that?
It's sort of my general assumption that anything that you can do between two chains, users are going to demand basically an equivalent experience between n chains. And so one question I have is like, how much of this is an OP stack thing versus how much of it just gets, if it works for the OP stack, then users are like, oh, great. Have second latency between chains. I want that everywhere. Make it for me. And then you have whatever. It's a risk product, but like you can price that, etc. That's one thing that's been top of mind for me when thinking about this.
Totally. I think that comes down to like a philosophical kind of question where if we think about it kind of from like a cost and like information theory perspective, I believe that it will always be cheaper for security between, blockchains or like rollups that have homogeneous properties. So like the same security model, right? So like two OP stack chains doing, low latency interop, I believe that it will always be simpler and cheaper than say doing interop between, an OP stack chain and Arbitrum Orbit chain. And this applies to like Arbitrum Orbit. Like it should be cheaper and simpler to do interop between two Orbit chains compared to like an Orbit and OP stack chain. The general Ethereum community is very supportive of low latency interoperability between rollup ecosystems. But to me, it's very unclear if like the incentives are set up for that to happen. The example that I always use here is historically, if you look at say like OpenCL versus CUDA, for like graphics programming, NVIDIA was able to move very quickly with CUDA and was able to develop something that was like proprietary, but like really, really good. And then, OpenCL like had to move slower because it was designed by committee, even though it was open. And CUDA ended up winning and being much more prominent than OpenCL. So my question is, when it comes to interoperability solutions, if we develop solutions that work between cross-rollup frameworks and pit them against solutions that work within rollup frameworks, which ones will be cheaper and which ones will win out? That's a little bit of context with at least how I've been thinking about this. Cool. So I'm going to hop right into it. I will stop every now and again to answer questions. So let me make sure I keep my eyes on the chat. Okay. So I'm going to skip through a lot of this like stuff, right? But you can see that one of the main reasons that we want to do like this interop, right, is execution became the bottleneck, right? Um, we can either vertically scale or horizontally scale. And my claim is that with vertical scaling, um, it's going to be very difficult to scale to the entire world, no matter how much we vertically scale. Um, so, like, we want to attack the problem from both solutions, both vertical and horizontal. And interop is about solving horizontal scaling. Okay, so let's see. Let me go down to the spec overview. Okay, so basically, how Interop works is we add some new pre-deploys, right? A pre-deploy is just EVM bytecode it's like a pre-compile, but it's EVM bytecode instead of native code. And the reason why we prefer pre-deploys over pre-compiles is that you don't need to add extra code to Foundry to make your simulations just work, right? So generally avoid pre-compiles because then you're going to need to implement code in every EVM implementation out there to be able to work with your chain. So we have these pre-deploys, right? And then these pre-deploys are tied to the derivation pipeline, right? So quick TLDR derivation pipeline, right? So I'm sure that all of you are familiar with this idea of state transition function, right? State transition function takes blockchain inputs and the previous state, and then it basically puts out the next state, right? And so um, the derivation pipeline is basically the process of preparing the inputs to the state transition function. So derivation pipeline scans over all possible data. It filters the data for data that can be considered part of this rollup, and then it maps that data into being structured inputs to the state transition function. So quick TLDR and derivation pipeline, right? And then the spec also includes this sequencer block building policy, right? So the true innovation in this design, the reason why I think this design is so interesting is because it does not have any global synchrony assumptions. There are no L2 to L2 force inclusion transactions. Everything is asynchronous, but things can become synchronous on top of this very simple protocol if block builders are able to coordinate, or the same block builder is able to build blocks for multiple chains. Then the last part of the spec is we have this contract in L1 called the system config. This contract is responsible for configuring the system, right? So you're able to add chains that you depend on and remove chains that you depend on by sending transactions to L1, configuring your system. So it's not a huge spec. This is pretty much the set of changes. Although the derivation pipeline changes are pretty extensive, and this does not include the fault proof. But just to be clear, fault proof is going to mainnet soon. Once the fault proof goes to mainnet, all subsequent releases, must also be fault provable. We will never enter a world where things are no longer fault provable. So we're working on the spec for the how to fault prove, interop. But we're sure that we can do it. At a TLDR, it's kind of just like, making the fault proof be able to fault prove many chains, and basically verify all the dependencies. Okay. Any questions, comments before I go like deeper into these particular topics? What's up, Wilson?
Quickly on the fault proof one, wouldn't that, I guess, two questions related to dependency set. First is, in what way are these chains becoming dependent on each other? And is there sort of you can't escape the vertical scaling assumptions. You sort of have found a new way to vertically scale because you're actually dependent on these other chains. And then second question is like, sort of same thing, but with like the fault proof lens of like, fault proof on one chain, you sort of have the ability to go back to the last agreed upon state. Are you now sort of dependent on the dispute that happened on this other chain? And you also have to roll back to your last agreed upon state based on that state.
Yeah, totally. So the dependency set, it is basically, you can say, these are the set of chains that I accept inbound messages from. And it's permissionless to say that you accept inbound messages from a chain. So let's say that your base, for example, and a bunch of new chains start up. Base does not need to say that they're willing to accept inbound messages from like these newcomer chains, right? That would just add like extra requirements to running a base node. But these other chains, they can, say that they're willing to accept inbound messages from base, but then they take on, having to add base to the dependency set, therefore meaning they need to run base. They need to like, sync base nodes. They need to like, make sure their nodes stay up to date. But to get into your point about, what the dependency set is in practice, right? It's you define the set of chains that you're able to accept inbound messages from. And what this means is you need to basically have RPC access to those chains. In future releases, we would like to relax this restriction of needing RPC access and move to a world where you can get all of the information you need to like verify these cross-chain messages via the P2P network, but that is out of scope for the initial release. With your question about vertical scaling versus like horizontal, technically you could think of two chains that depend on each other as like parallelism, and we don't necessarily have parallelism in like an EVM equivalence kind of context yet, like true parallelism. So I do think that it is like, in some ways it's better than, just only focusing on like vertically scaling, like a single chain, if that's what you're getting at.
Yeah, that makes sense. Yeah, it's sort of if you max out one at a gigagas per second, does that mean that you can run two at a gigagas per second with some dependency on each other? I'm not totally sure. But yeah, and
you totally could.
Okay, yeah.
Is it okay if I move on a little bit?
Sure. Yeah, go ahead.
If you want to leave your questions in the chat, I can make sure they get answered. But okay, so right here we have a little glossary, right? So this is just like standardized language, right? We have a source chain and a destination chain, and then we have an initiating message and an executing message, right? So source and destination chain, pretty straightforward. Initiating message, executing message, right? These are like the core primitives of the Interop protocol. An initiating message is simply an event that is emitted from a source chain. So the core primitive here is an event. An executing message contains that event and is sent to a destination chain, right? So basically what Interop allows you to do is ingest events like logs, you know, from one chain to another chain. And what's nice about this is that, you know, smart contracts already use events today. No smart contracts need to change to be able to be interoperable. The interop protocol literally just lets you, you know, read events from other chains. So we talked about dependency set already a little bit. The cross-chain message. The cross-chain message is just like the kind of, you know, this both the initiating message and the executing message. Okay, so going into this right here. So an initiating message and an executing message, right? So the executing message, right? How do we ensure integrity of the initiating message, right? You could imagine if this was like a ZK, like a ZK solution, you could like, you know, provide like a ZK proof, right? And say, you know, hey, other chain, this is a proof that this log exists, right? But we, you know, don't have to worry about having the kind of proof gen and verify in our hot path, right? We're building an optimistic system. So we have this executing message, and okay, right here. So you can see here the executing message, right? In practice, what an executing message is it's a call to this contract, right? This execute message function on this pre-deploy, right? This pre-deploy is called the cross L2 inbox, right? And when you call this cross L2 inbox, it takes an identifier, a target, and a message, right? So in practice, this is the identifier. The shape of the identifier is right shown on the slide. And the identifier is simply a pointer to a log. So when you call this function execute message, basically what you do is you include the message, which the message is the serialized log. And then you include the identifier, which is a pointer to that serialized log in a remote chain. Technically, the spec allows you to also point to your own chains. You can ingest events from your own chain through this. It just works like with the design of default proof. But like for simplicity's sake, you know, we can just think of the invariant that the chain holds, the fork choice rule, is that all calls to execute message have the identifier correctly points to the message, right? So anytime that this execute message function is called, if the identifier does not match the message or like the serialized log, then that block gets reorged out. So just to clarify, this identifier, right? It's a pointer to a log. So to like uniquely identify any log across any chain, you need a chain ID, right? Which this implicitly is like an RPC URL, right? You need a block number and you need a log index, right? With these three pieces of information, you can look up in a remote chain to basically get the log, right? And then verify that the log is correct. Does this make sense? I'm going to pause for questions, comments.
Can you clarify? You said reorged out, and I guess I would have thought the transaction would just revert. Could you explain more there?
Totally. So there's this paper. It's not necessarily a paper. It's more of a blog post by Barnaby at the Ethereum Foundation called "Seeing Through the Eyes of the Protocol," right? And it's all about this idea of the protocol can only like regulate or modulate things that it is aware of, right? So from within the smart contract, from within the EVM context, there is no legibility into the fact of this particular message, the serialized log, corresponding to this identifier, right? So that legibility is able to happen from within the derivation pipeline, not within the smart contract. So the idea is within the smart contracts, we optimistically accept, any transaction, and then the sequencer knows that if they include a transaction where the identifier does not match the message, right? Because the core invariant is that every transaction that's included, the identifier must match the message. The sequencer knows that there's risk, so the sequencer must validate that the identifier and the message match each other before including the transaction. So that's basically what I did with this like pseudocode right here, right? You can see this like Pythonic pseudocode. Great question about new griefing. So when we originally were working on the spec, we were very worried about griefing. So we added this thing, we called it the only EOA invariant. And, smart contract wallet developers hated us, but we were afraid of griefing. And basically we had this invariant that was in the smart contract, which enforced, TX origin is equal to message sender, right? And this guaranteed that we would be able to statically analyze the transactions, right? And with 3074 being CFI for Prague, which is expected to ship to L1 in Q3 or Q4, we decided that we need to, there's no way to guarantee only EOA. So we're just going to lean into, smart contract wallets. And, I think, in my opinion, the like kind of OP-ACK way is to, lean into hard problems. And even if it's, challenging, we can solve denial of service if we architect things in the correct way. So basically, if you're a sequencer, right, you need to like verify all of these like incoming transactions before you include them in a block, right? And if we think about L1 with like PBS, right, like we know that block builders are like very specialized, right? And there's like an economy of scale to block building, and it's okay for block builders to be centralized. It's kind of like, going to be very difficult to like keep this highly specialized role decentralized. We can try our best. L1 is trying to keep it cheap to run a validator, ensure it's cheap to, the ability to propose, right? And then let the block builders like specialize, right? So like this, in our eyes, is like one block builder specialization where they can build the infrastructure to verify all of these transactions to make sure they're not including a transaction that, calls this pre-deploy with an identifier that does not match the message. Um, okay, I'm going to pause for a second and then I'm going to look at the messages. Okay. Okay, I'll keep going. I would love to respond to all of these on like the GitHub discussion board that I created. Just trying to like curate more knowledge in public so that we can scale knowledge. And also there's like amazing, talented people, joining the ecosystem. And I would love to like have all of your feedback. I think that y'all will come up with like amazing ideas and would probably solve things. What's up?
Yeah, Mark, I have one question. So like for the executing message, like what if the original message is reworked out from the chain?
That's a great question. So that is a level of risk that a sequencer needs to take on, right? If the sequencer is willing to take on the risk of a reorg, they can include the, they can include a log that was emitted, in block n minus one, but it's that sequencer is taking on the risk, right? So depending on how much you as a sequencer, depending on how much you trust other chains, um, how much you trust their pre-confirmations, determines the latency at which you should include these cross-chain messages. What's up, Daniel?
Just to make sure I follow then, like let's imagine you had like a really low throughput chain that only batches every like hour. And you have a high throughput chain that maybe batches every minute and gets finalized after like 20 minutes. In theory, if you accepted on the high throughput chain, if you accepted like low throughput chain messages like instantly, you could have an unsafe reorg cause a finalized reorg. Is that what you're saying, that you'd have to choose? Be like, I only trust this chain?
Yeah, so like basically what you're getting at is like the finality of one chain is now tied to the finality of another chain. And in the case of one chain being like a slow batch submitter, right? Because low throughput, that the accepting, executing messages like inbound messages from that chain is risky because their data has not been like finalized or batch submitted to L1, and there's not L1 economic security on top of that. So they can equivocate, and basically, if they do equivocate, then any chain that has accepted logs, like unsafe logs, logs that where like the data hasn't that created those logs has not been batch submitted, like if what gets batch submitted is different, then it will 100% cause a reorg, right? And we update the derivation pipeline such that like we change like what the definition of like safe means, right? Like we have this like unsafe and safe distinction, where unsafe right now is just data that has has reputational based pre-confirmation security, right? There's no economic security. It's just reputational based. And then when that's unsafe. And then when the data is posted, then the data is on L1, then it transitions from safe to unsafe. And now you can consider that data final, right? You can trust that that data has, it's not going to change, right? So we introduce a new label called cross unsafe, right? So there's this idea of unsafe and then cross unsafe and then safe. And there should be a slide on this, but the TLDR is that we change the semantics of like, what are the invariants that must be held to transition from unsafe to cross unsafe, and then from cross unsafe to safe. And the best mental model for this is to imagine a graph. You are unsafe. Okay, so first the graph. The graph is it's a directed graph, and it's basically it is all cross-chain messages, right? Between all of the chains in your transitive dependency set. Because you have your dependency set that you accept inbound messages from, and then you have to also take into account the dependency set of all of the chains that you depend on. So like you need to build up this like transitive dependency set, right? And then what you need to do is you need to like build a graph to find all the cross-chain messages, right? And basically, you are considered unsafe when you do not have a view of the full graph for a particular block. When you go out and you basically get a full view of the entire graph, and you're able to basically say every cross-chain message, I know that the identifier matches the message, and they're correct. When you're able to go out and verify that for every edge in your graph, then you can then transition a block from being unsafe to cross unsafe. And then when every single edge in that graph, when the data is posted to L1, then you can then migrate from cross unsafe to safe.
Does this mean that you like, because you don't have control over your dependency, like your safe time is kind of like dependent on your dependency as well?
Totally. That's a very great intuition. Like now, finality depends on other chains, right? So to solve for this problem, we have like a few different ideas, right? Like you could imagine, some sort of like, shared batch submitting, where chains have the ability to like aggregate their batches together. This is like one design space, and then you can like get like the compression benefits, and kind of, take the batches of small chains and like batch submit them faster. So that's like one design space. Another design space is starting to, okay, so I call this meta batches, kind of like meta transactions, but like meta batches. This design space involves basically, you start to blur the lines between the pre-confirmation signatures and the signatures that are submitted as part of, or the signature that is used to authenticate the validity of the batch. So what does this mean, right? Right now we have this idea of the P2P sequencer key, and we also have this idea of the batcher address, right? The P2P sequencer key, that's like the, that's the key that is used to sign for pre-confirmations. And the sequencer signs the block and sends it over the P2P network. And if you receive PDP traffic where it has the signature, then it's considered, valid pre-confirmation. That's an unsafe block. Then we have this idea of the batcher address, saying batcher hash is like what it's called, smart contract, but the batcher address, right? So this is the key that sends the batches to L1, right? So what this means is there is only one entity that can send the data to L1. It is that entity that holds that key. This is just assuming that the key is not widely shared, you know, but let's just assume that the key is like only held on and known by one entity, right? This entity is just, you know, signing the data and publishing it to L1. So what we do is we figure out how to meld the P2P key and the batcher key such that any chain can submit data that they depend on to L1. And we could do this through like some sort of BLS aggregation scheme where we could like aggregate a bunch of signatures together and then stick the BLS SIG in the batch itself instead of relying on the top level ECDSA key to like authenticate, you know, the validity of a batch. It's a little bit of a rabbit hole. There are solutions for this. We just need to like, you know, iterate on them. Does that answer your question?
Yes.
Cool. All right, so I'm going to continue. We already talked about the dependency set. Okay, so this is the cross L2 inbox, right? This is one of the new pre-deploys, right? We removed this only EOA for denials of service protection. We're actually in the process of implementing the smart contract changes for this now. And there's an open specs PR for this change. But the idea is that, you know, there's two invariants that are left that we still, you know, require, which is the initiating message cannot be from the future, and the initiating message must be from a chain in the dependency set, right? So this is enforced on chain. This is like the information that's legible to the chain. And all the other information is like only legible from within the derivation pipeline. The idea is with removing this only EOA for denial of service protection, it will make it more expensive to build blocks. It technically introduces this problem where if you are an interop chain, you have interop enabled, then that means that you technically require EVM execution to know if you should accept the transaction into your mempool. This is very bad. So, like I said previously, you know, the OP-AC way is to, you know, focus on engineering solutions that are scalable. I believe that we can solve this denial of service by, you know, building a horizontally scalable backend that we delegate all transaction validation to, right? So if somebody is denial of serving us, we can, you know, spin up additional copies of this microservice and basically, you know, eat the like denial of service attacks. And if that doesn't work, then we have to, you know, resort to things like IP bans. And if that doesn't work, then we have to resort to something like, you know, Flashbots' identity with rate limiting, where, you know, Flashbots rate limits based on how many bundles you land. So we can do something similar. But the general idea is that we can solve this denial of service, you know, attack. We just, you know, can't be afraid of it. And we have to design things in a way that we can horizontally scale our defenses against these sorts of attacks. Okay, I'm going to pause now. Any questions, comments, anything unclear?
Nothing super unclear, but I'm wondering if there's any like known toy sort of like use case that we can think about just to make it a little bit more tangible, like how an actual application flow might look.
Totally. So I have two example use cases, right? And kind of like what I said at the beginning of this talk, I do think that this is going to require a big rethinking about how we go about developing smart contracts, right? Because we develop smart contracts as these like modular applications where all the smart contracts live on the same chain. And I just don't think that it's possible to scale to the full world if we continue with this being the architecture. So I believe that the architecture in the future is going to be decomposing these monolithic smart contract applications such that the most gas intensive parts of your application can be horizontally scaled. And then what we can do is we can ensure that the fees basically are equal to about the cost of running the hardware, right? Because we can auto scale more chains, right? Like that, I think is like the vision, because as demand goes up, then we can make supply go up as well. And we can equilibrium around like, we can smooth the base fee across many chains. And like, that's the ideal vision for this. So in practice, what does this look like? I have two examples. One is an NFT marketplace. So you could imagine, let's imagine something like Seaport, right? But it's designed specifically for this interop world, right? So let's pretend that we're making NFTs for like an extremely popular IP, like, Pokemon, right? People love Pokemon. There's like, millions of people all around the world that, play Pokemon. And if they all wanted to mint an NFT at the same time on Ethereum, Ethereum would fall over, right? So you can imagine that what we do is we develop an NFT marketplace, and you can kind of, it's sort of like designing like a Web2 application where you have microservices, but each microservice is a set of horizontally scalable EVM chains that are responsible for one part of the application. So for the NFT example, you could imagine a minting engine where we write some sort of ERC 721 new standard. I don't know exactly what, but we write an NFT contract that can mint in a horizontally scalable way, where there's the assumptions don't assume that the entire state of the contract is on one chain, right? So we have this minting engine, right? So users that want to mint, they're probably ideally they're using a smart contract wallet, and they have like an intent or something that says they want to mint, right? And then their intent gets settled into the minting engine, right? And then so like this minting engine is like literally using all of its gas to mint NFTs. And that's all it does, is it's just constantly minting. It's constantly at max capacity or like some target capacity. And it's just minting and minting and minting. And then we kind of have the matching engine. This is like, Seaport, right? We figure out how to shard Seaport such that, anyone that wants to put a NFT up for sale, right? They're able to like go into the UI and just say, I want to sell this NFT at this price. Then that would just kick off a transaction, like probably like an intent to meta transaction, whatever, that would, move your minted NFT off of the minting engine over into the matching engine, right? And then this matching engine, you could imagine, this is just like, constantly, facilitating trades and constantly facilitating, adding orders to like an order book, right? So like we have like these two kind of different clusters that are responsible for different, parts of the application. And then we can design the smart contracts in a way on both so that we can like take advantage of things like, block STM, like, optimistic parallelization, things like that. And then you could imagine that, we have like another place, which is like another cluster that's more like the long-term storage, right? And then, maybe if you don't do anything for a long time with your NFT, the system can like, sweep your NFT over to the long term storage chain, and then it can sit there. And from the point of view of your wallet, we write a RPC adapter that is able to like virtualize all these different EVM chains to make it seem like it's one chain. That was a lot. Curious if there's any comments.
I think it makes sense. One sort of facet of this new architecture that you're describing, and I'm curious if you think it's going to be like become de facto or like prevalently what happens is like proliferation of app chains or dApp chains, really, instead of like lots of throughput across lots of sort of generalized chains.
Totally. I think this is a great question. And yeah, I just want to be clear, like I might be completely wrong. This is just like my personal opinions, but like I do have like a lot of conviction on this design space. I think it's very exciting. But if anyone disagrees, would love like, to debate or like love to hear new perspectives, because I have no idea if this is going to be like what takes off or not. But basically my belief is that the idea of like chains is a monolithic concept. And I think that we will like progressively move away from the idea of chains, and we'll move towards the idea of verifiable compute as a resource as part of your application. And I think that like with L1, it will always be like a modular approach. But I think with L2s and like L3s and plasmas, whatever, I think that's where we start getting into this world where, it doesn't make sense to have like a single flagship chain, but instead, you have like a set of chains that are provisioned per application and their architecture is set up in a particular way. And then you like settle them maybe you settle them to like your flagship chain. Or like, maybe you have like your flagship chain is just the like, you figure out a way to scale your flagship chain horizontally, and then everything's branded on that flagship chain. Just kind of like brainstorming ideas. I don't really know. Does that make sense?
Yeah, it's very cool. It's a very different world. But yeah, I think I understand what you're saying.
Cool. Any other questions or comments? Cool. All right, so I'm going to move on. So basically, from the point of view of the smart contracts, we have layered abstractions, right? So, we have this cross L2 inbox, and the primitives for this cross L2 inbox, it literally just takes events. It's able to read in events from other chains, and from the smart contracts point of view, you have assurance on the integrity of these events actually being correct from other chains because of the fork choice rule, right? The fork choice rule will reorg out, messages that don't correspond to their identifier. So the cross L2 inbox gives us this primitive of I can trustlessly read in the events of other chains. On top of this, we have the L2 to L2 cross-domain messenger. This is like a higher level kind of like, abstraction that makes it much easier to like send a message to a particular chain, right? So this gives you replay protection and domain binding. So what that means is like domain binding basically is like you can only, play this transaction, or this, like, you can only execute the message on like one chain, right? So like you commit to the chain ID that you want to, like, call, right? And the messenger ensures that you can only play this transaction once, and you can only play it on a particular chain, right? Like not all applications will want this, but many common applications today, like asset transfer, will want this. So this smart contract is meant to be like the primitive for our superchain ERC20 token, right? ERC20 token is very popular. So we want to have an ERC20 token that is portable and fungible across all of these chains in the superchain, right? So the superchain ERC20, it will directly interact with the L2 to L2 cross-domain messenger to ensure that when you, basically burn and mint your ERC20, it ensures that like you can only, like, mint it on the chain that you want to, if that makes sense. I'm going to pause for a minute. Any like questions or comments?
So is calling to the cross-domain messenger permissionless?
Yep. It's 100% permissionless.
And then it's just writing to like a mapping on that ID.
Yeah. So it's writing to a mapping exactly to give you replay protection. And if you want to add something like permissioning, then you would just add that permissioning at one abstraction higher on the contract that is either called by the cross-domain messenger on the executing side or calls the cross-domain messenger on the initiating side.
I've been thinking about, it seems like a common thing people will want to like attach some like payment to their message to pay somebody to relay it for them. I'm curious if you've thought about that and making that into the core.
Yeah, totally. So all of these functions are payable. So it's 100% possible to send along payments and then have, abstractions on top of these messengers handle routing the payments. With the removal of the only EOA invariant, you could imagine using a 4337 bundler to basically, send a bunch of executing messages, and you could imagine some scheme where like there's like a paymaster. I'm not an expert at like the implementation of 4337, but I could imagine there's like some sort of scheme where there's a paymaster that pays for, executing the messages on behalf of the user, and then also like gets paid back by the user in some way. Cool. Yeah, so I just want to make sure that I hit all of like the core ideas. I talked about like, the core primitives of like the initiating message and the executing message. I talked about the kind of way that the fork choice rule ensures that you can trust these executing messages from within your smart contracts. I kind of talked about the dependency set and the management of the dependency set. I talked about like an example application. I think another fun example application is like an on-chain order book. Like, my personal dream is that the centralized exchange eventually becomes a on-chain fully by, creating an on-chain order book, using like an interop scheme where you can like horizontally scale the number of, EVMs necessary to like facilitate trades at any moment. I just think that this is so interesting. I do think one of the downsides is that it's going to be like way more expensive relative to like running traditional Web2 infrastructure. But you know, we can optimize over time. And yeah, I talked about like some the pre-deploys, abstractions that developers can plug into. I'm curious if there's any leftover confusion or comments or anything that people would like me to like go into more.
Any sense of timelines that you're pushing for?
Yeah, totally. So we're trying to ship this by Q4. Right now, our team is really small, but we're hiring some more people. We're going to be starting interviewing over the next couple of weeks. But we're hoping to be able to have this ready for production in Q4. Yeah, and like to me, this is very, very interesting because one of the things that I find the most interesting about this is the ability to build atomic composability on top of this, right? Because the spec only says that the initiating message cannot be from the future, right? So what this means is that the initiating message can be from the same timestamp. It can technically, you know, if you try to like linearize like two chains, right? All the transactions that happen at the same timestamp between two chains, like technically, like you can't like linearize them. Like, you know, they have the same timestamp. So like the first transaction in, you know, chain A and like the last transaction in chain B, like you can't really compare them. They have the same timestamp, like they happened at the same time. So like, you know, what this property allows us to do is we can build atomic composability if we have like the same entity basically build blocks for two chains at the same time, right? Where as they're building, you know, a block for chain A, they like are emitting events, right? And then in chain B, they're building a block, and then they're including references to these events, right? So these blocks are being built at the same time. You can reference these events, you know, between blocks at the same timestamp. So if the same entity is building blocks for multiple chains, or if they're different entities and they communicate and collaborate with each other, either, you know, abstraction works, then, you know, we can build transactions that call back within the same, you know, block. So this creates like an interesting kind of pattern where you could imagine that you have like some expensive on-chain computation. You could imagine like, you know, taking off your compute and then it like, you know, goes off and it uses a ton of gas on another chain and then it finishes and then it comes back. You could imagine like a design pattern like that. I think that there's all sorts of like fun things that can be built, and it's just really like, you know, actually shipping this and getting it into the hands of like creative people. This makes the super chain super. Yeah, there, Ricken. Cool. Well, I believe that we are a little bit over. I don't necessarily have a hard stop, so I can stay on for like another 10 or 15 minutes if anyone has any questions, but if not, we can end it. Thank you, Andrew. Cool. So one thing that I want to share is basically if anyone wants to follow along or learn more or contribute, we have our specs. So this is specs.optimism.io. And if you go to this website, you can see chat with us on the discussion board. If you just follow that link, it takes us to the specs discussion board on GitHub. And there is a catch-all topic for Interop. And Roberto has already left our question on it. So thank you, Roberto. If anybody needs any clarification or wants to ask questions on progress, roadmap, or anything, feel free to leave a comment. And the goal is to kind of move to the public, right? We want to make our roadmap and ideas legible for the public so that we can nerd snipe more builders. Cool. Well, that's it for me. If nobody else has anything, I'm happy to answer any questions, continue the conversation if anyone has anything to add. Otherwise, I'm going to end the recording and then call it. Cool. All right, I'm going to call it.